Hello everyone, and welcome to my channel. This is a channel that is dedicated to educational upliftment and just informing the public about certain things that they may not know about that could be important to them. If they studied up and exercised their noggin a little bit, they might find some treasures hidden in this channel. And today is our 384th video that we've done on the reciprocal system of theory. And this is a theory from Dewey B. Larson, who brought it to the world in 1959 when he put out his two fundamental postulates. And then after that went through a period of deduction, where he went step by step from his postulates to what he calls his theoretical universe. If this, then that. If this, then that. And so if my postulates are correct, this is what my universe would look like. And then in his books, he compared his universe with the, empirical universe, measured and documented and compiled by various scientific tables from the legacy scientists. And through their telescopes. And turns out Larson actually didn't need a multi-billion-dollar telescope or atom smasher to come up with the same results that the scientists did. He got it just out of his head from theory only. And so I think that's kind of worthwhile. And today we are embarking on our 6th episode of doing his paper called How Much Do We Really Know? And this is kind of a history of science article that he wrote, just about how legacy science tends to exaggerate what they really know, and he kind of throws some cold water on the pronouncements of science, particularly like in the textbooks written by the rank and file scientists, where the actual top scientists in the field, they actually know that they don't know a whole lot. And their latest theories are generally just hypotheses. They're the best that they've got so far. And that's fine. And that's something that you can move along with and you can proceed. But when you claim that you have it all figured out and you don't, then you are stifling science, and that's the essence of unscientific. And so that's kind of what he's getting into now. He talked last episode a lot about the nuclear theory, and this goes contrast with his. This kind of goes hand in hand with his book called "The Case Against the Nuclear Atom." Larson claims that the atom has no nucleus, and the little thing that you're bombarding that seems to be stopping particles and stuff is not the nucleus, it's the atom itself. And that's the whole thing. And then there's a lot of space in between the atoms. I haven't read that book, so don't quote me, but just from going through yesterday's material. Now today he's going to go toward the electrical theory of matter. So we'll see where he goes from there. But first I just want to give you a quick once over on the reciprocal system itself. Particularly his two fundamental postulates. The first postulate is, and the first postulate is really 90% of it or more, that the universe is composed of one component, motion, existing in 3 dimensions in discrete units and with 2 reciprocal aspects, space and time. And then the second postulate is the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute and its geometry is Euclidean. Now, set aside the second postulate, there's a lot of dispute about that, and even with Larson, Larson used Euclidean geometry, but he was aware of the other geometries as well, but he kind of just used Euclidean geometry because he didn't want to have to explain even more. You know, sometimes when you're the author of an original theory, you're spending so much time backtracking and going over the stuff that people need to unlearn, that your own original theory gets convoluted in the process. And I think that's kind of where Larson was with the Euclidean geometry, is that he I think was aware that there are other kinds of geometry out there that were more inclusive, but went with the Euclidean geometry because it was just, it did the job. And the Euclidean geometry does do the job almost in all cases or whatever, but one of his followers, Dr. Bruce Perret, came along and changed that to projective geometry, which is, Euclidean geometry is a subset of projective geometry. So it's not really saying that it's not Euclidean geometry, it's just that the Euclidean geometry doesn't apply in every single case. Now, in terms of the first postulate, I would kind of just restate that as the universe is not made out of matter. It's not made out of energy. It's not made out of the fundamental forces. It's made out of motion. And specifically, it's made out of something that is called scalar motion, which is a motion that has a magnitude, but it has no specific direction, which you can envision using a balloon with dots on it. If you blow up the balloon, all the dots are moving away from each other, but they're not moving in any specific direction. Each dot is moving away from each other dot. And in fact, even the spaces, the locations between the dots, are moving away from all of the other locations between the dots. It's really just the progression of space itself. Space itself is moving apart and in all directions. So the universe is not made out of matter, energy, or force, or anything other than motion, scalar motion. And scalar motion is the relationship between space and time. Therefore, space and time are reciprocals of one another, meaning that they are identical to one another, except that they are basically in reverse order. They have the same qualities. They do not exist separately. They only exist together in motion. They have their scalar aspects, which Larson calls clock time and clock space. And they have their stationary aspects, 3 dimensions in a stationary frame. And Larson refers to that as coordinate time, coordinate space. And motion is basically a fraction with space or time as the numerator and time or space as the denominator. And space or time both can come in multiple dimensions. And so you can have, some coefficients like pressure, time over space to the 4th power, or matter, time to the third power over space to the third power. Or you can have the more simple relations like speed. Speed is just space over time. Energy is time over space. Acceleration is space over time to the second power. Force is time over space to the second power. And so on, all our fundamental scientific quantities are expressible exclusively in terms of space and time. And space and time both come only in discrete units. You have to have a full unit of space before you have any space. You have to have a full unit of time before you have any time. And if you have 1 unit of space in 1 unit of time, space over time being speed, you have the speed of light. The speed of light is what Larson refers to as unit speed. 1 over 1 equals 1. And unit speed in Larson's universe of motion is the background speed of the universe. The speed of light moving outward in all directions is what Larson calls the progression of the natural reference system. And this is what exists in this universe when you have absolutely nothing. So when you have absolutely nothing, you have 1, and you have the motion outward in all directions at the speed of light. That is the state of rest of this universe of motion. And that contrasts sharply with the legacy scientists who make their measurements from 0. Larson makes his measurements from that unit speed. It can be either faster or slower than the unit speed. That means that half the universe is moving faster than the speed of light, and half is moving slower. Just like with a reciprocal, when you have 1 at the center, on one side you have greater than 1, 2, 3, 4, 5. And on the other side you have less than 1, 1/2, 1/3, 1/4, 1/5. And the less than 1/2 Larson refers, or less than 1, Larson refers to that as the material sector. And the greater than 1 he refers to as the cosmic sector. And they have the same identical qualities, except that they are in reverse roles of space and time. So in the material sector, you have coordinate space, 3 dimensions of stationary space, and clock time. The clock is always getting later and later and later. In the cosmic sector, by contrast, you have coordinate time, 3 dimensions of stationary time, and you have clock space. Space is always getting farther and farther and farther apart, like an expanding balloon, dots on an expanding balloon. Okay, that gives you just the outline, the skeleton of where Larson got started from with his reciprocal system, mainly the first postulate. Now we're going to just get into his this installment of his paper. Just what do we really know? Or no, I think it's how much do we really know? And again, he's going to be talking about the electrical theory of matter. The electrical theory of matter originated from the observation that certain substances, on being dissolved into 2 parts, separated into 2 parts, or ions, one bearing a positive charge, the other a negative. Later, various phenomena, such as the thermionic emission of electrons, the photoelectric effect, etc., which involve ejection of electrons from matter, were discovered. Since the experimentally observed electron is a negatively charged and highly mobile particle, it was concluded that ionic charges were due to an excess or deficiency of electrons relative to the number which the atoms presumably should contain in the neutral condition. This is plausible and in many respects a rather attractive theory, but for present purposes these aspects are irrelevant. what we want to know is, does this theory constitute positive knowledge, as the textbooks contend? The answer to this question is definitely no. Close scrutiny shows that, here again, we have nothing more than a very questionable hypothesis. Looking first at the matter of ionization in solution, it is clear that this is the same kind of a situation that exists in the case of electrons which appear among the atomic disintegration products. The theory that the electric charges existed prior to the time that the substance dissolved is only one of the possible explanations of the observed facts. It is not even the best of the readily available explanations, because if we accept it, we find it necessary to conclude that there are two different ionization mechanisms. The general chemistry textbook on the author's desk admits that ions are formed not only by the so-called ionic compounds, but also by compounds that are definitely not ionic, and goes on to say, quote, if ions are not presently in an electrolyte before it is dissolved, they must be formed from the molecules of the compound as it dissolves, end quote. But as long as we have to assume that some ionic charges are created in the process of ionization, it is clearly within the bounds of possibility that all ionic charges are thus created, an explanation that has a considerable advantage from the standpoint of simplicity. The existence of charged particles in solution is therefore far from being proof of the existence of electric charges in undissolved matter. Similarly, everything that is known about the photoelectric effects, the thermionic emission of electrons, and other phenomena of this kind is entirely consistent with the hypothesis that the charged particles are created in the process. Obviously, we cannot regard any theory as having been verified by experiments if the experimental results are equally consistent with some different hypothesis, and hence none of these results qualifies as a proof of the electrical theory of matter. At the time the nuclear atom was originally conceived, the idea that electrons might be created in some physical process seemed so remote that it was probably never even given consideration. But today it is commonplace. Such creation is currently being observed in a great variety of processes, ranging all the way from production of a single electron-positron pair by an energetic photon to the production of a shower of millions of particles by a cosmic ray primary. We now find that the electron with which we deal experimentally is something altogether different from the atomic building block envisioned by Rutherford. It is a tangible but evanescent particle that can be produced or destroyed with relative ease. If we take a broad view of the entire picture of the electron, including both theory and experiment, it is apparent that there is a curious dichotomy in the usual concepts of this particle. The experimental electron is a definite and well-defined thing, notwithstanding its impermanence. We can produce it at will by specific processes. We can measure its mass, its charge, and its velocity. We can control its movement, and we have processes by which we can record that path that it takes in response to these controls. Indeed, we even have such precise control over the electron movement that we can utilize it as a powerful means of producing magnified images of objects that are too small for optical magnification. In short, the experimental electron is a well-behaved and perfectly normal physical entity. On the other hand, the theoretical electron, which, according to currently accepted theory, is one of the constituents of the atom, is a very strange phenomenon. Don't quite get that sentence, but there's probably a typo in it. It presumably moves in an orbit around the atomic nucleus, but we cannot locate either the orbit or the position of the electron in the orbit. The best we can do, experts say, is to compute a probability that it might be found at a certain location. Unlike the experimental electron, this theoretical electron does not follow ordinary physical laws, but has some unique and unprecedented behavior characteristics of its own, including a strange and totally unexplained ability to jump from one orbit to another with no apparent cause. Furthermore, as already mentioned, the leading theorists of the present day tell us that it cannot be accommodated within the three-dimensional framework of physical space. It must be regarded merely as a symbol rather than as an objectively real particle. Under the circumstances, it becomes pertinent to inquire whether there is actually any adequate justification for identifying the theoretical electron of the nuclear atom with the experimental electron. Once this question is asked, it clearly must be answered in the negative. Certainly, we cannot logically contend that two entities that differ widely in practically every respect are actually identical. What has happened is that the theorists originally started out with the assumption that one of the constituents of the atom is a particle identical with the experimental electron. But as more and more information was accumulated, it became clear that the properties of the experimental electron were incompatible with the requirements of the hypothetical atomic constituent. The assumed properties of the atomic electron have therefore been progressively modified to meet these requirements until they now bear no resemblance to those of the experimental electron. It is high time, therefore, that the pretense of identity should be abandoned and that the electron constituent of the nuclear atom should be recognized for what it is, what it actually is, a purely hypothetical concept which has no relation nor resemblance to any particle that has been observed experimentally. Naturally, the physicist is reluctant to take this step, in spite of the absurdity of claiming identity for two particles which have practically nothing in common, since the modern theory of the atom rests on the assumption that it is a complete structure built up by a combination of some of the matter particles, some of the smaller particles, which have been observed experimentally. Once it becomes necessary to admit that the atomic electron is a purely hypothetical creation, unrelated to anything that has ever been observed, an abstract thing, no longer intuitable in terms of the familiar aspects of everyday experience, as Henry Margenot describes it. This basic concept of the atomic structure is destroyed, and the whole theory crumbles. After having been so confident for so long, the physicists find it very distasteful to face the realities of this situation and to admit that the concept of an atom constructed from known particles of subatomic size is no longer tenable. But this is exactly the kind of catharsis that we need in order to clear the way for a new physical theory adequate to meet present-day demands. After all, how can we expect a theory based on the assumption that matter is composed of permanent, indivisible elementary particles, similar in all respects other than size, to the atoms of Democritus. To give us the right answers in an age when it is admitted that we do not really know how to define an elementary particle, but we do know that no particle is permanent, that all particles, large or small, material and non-material, are subject to exchange of identities in a bewildering variety of transformation reactions. Actually, we must go still a step further. Not only is it now clear that the constituent parts of the atom are not known particles, such as electrons, it is also becoming apparent, as mentioned earlier in the discussion, that the atom has no constituent parts at all. Of course, the immediate reaction to this statement will be that it is preposterous, since we can readily break the atom into separate parts. But let us examine the situation a little more closely. Suppose we have a certain object moving with a high velocity, and we then detach the velocity by transferring it to something else. Must we then conclude that the original object consisted of two separate parts, and that we have broken it into its two constituents? It is very doubtful whether anyone would ever support such a conclusion as this. But if we compare this situation with the breakup of the atom, it is evident that the only basis on which we can claim that we have done something different with the atom is by contending that the parts which are detached from the atom are inherently of a different character than the motion which was detached from our hypothetical object. Can such a contention be justified? We have found that both the proton and the electron can be transformed into radiation simply by contact with their respective antiparticles. All matter seems to be radiation, says Morse, and so far as we know, radiation is nothing more than a vibratory motion. Can we say that the proton is inherently different from motion when we can transform it into motion? Are we not forced to the conclusion that the atom could very well be an integral entity endowed with specific amounts of various kinds of motion, or something equivalent to motion, and that what we call breaking it up into parts amounts to nothing more than detaching portions of this motion or the equivalent thereof? And is it not true that the trend of discovery in the subatomic field is driving us slowly but inexorably in this direction toward just such a conclusion as the foregoing? Already it is evident that there must be some common denominator, not only for the particles, but for radiation as well. Particles are materialized from radiation and are annihilated back to radiation again. Protons become neutrons and vice versa. Mesons are created from kinetic energy and ultimately decay into electrons and neutrinos. The atomic reactors transform mass into energy, while at the same time the particle accelerators are busily engaged in converting energy back into mass. This interchangeability between the elementary particles, between the particles and radiation, between mass and energy, has already administered the coup de grace to the popular theory that the universe is constructed from different kinds of elementary building blocks, even though the inertia of customary habits of thought and a strong attachment to familiar ideas are delaying the general recognition of this fact. It is already evident that the raw material of atom building is more analogous to modeling clay than building blocks. Okay, I think we're going to stop there and do the rest tomorrow. I think we're getting close to the end of this article. Yeah, we'll finish it up tomorrow and maybe discuss a little bit. But yeah, just for the record, in Larson's system, there are two kinds of electrons. There is the uncharged electron, and then there is the charged electron. That's quite different than legacy science. The electron in Larson's system is a rotating unit of space, and the uncharged electron is referred to as by legacy science as electric current. And static electricity is the charged electron. And the charge is a rotational vibration. And so the uncharged electron is the rotating unit of space, and which moves through matter. Matter is made out of time, and the electron is made out of space. And so space, the relationship of space to time is motion. And so an electron moves through the atom, but it can acquire a vibration while in matter, and then it becomes stuck. And that is the charge. That's the way I understand it, at least. And maybe he'll clarify that as we go further. But and certainly he'll clarify that when we get into his book, Basic Properties of Matter. All right. Well, thanks for tuning in today. And come back tomorrow for the rest of this paper. And otherwise, have a great day. I know it's New Year's Eve here. And tomorrow is beginning of 2024. Just wanted to say that in the writings of Zecharia Sitchin, the ancient aliens guy, Nibiru Sumerian tablets person, according to his chronology, the Sodom and Gomorrah episode occurred in 2024 BC. So here we go again, and looks like kind of a mirror of where we're headed, but it can be a great beginning as well as the ending of something. So, you know, I think we just need to focus on, you know, it's the end for them, and it's not the end of the world for us. It's the end of the world for them, and we can begin with a great beginning if we can move through this. All right, have a great day.